Our first example is example 1 on page 9-20 of your handout. So there's two disks rotating in the same direction. They're pushed together, and what we want to find is the final omega of the combination. So first things first, let's think about this. Is it conserved? Well, I'm not told that there is an exterior force. If I'm not told that there's an exterior force, I can't assume that there's some sort of torque acting on the system that is going to change this momentum. So therefore, this is going to be a conserved quantity. So that's the first question I want to ask myself. And then the second question I need to look at is like, okay, we're doing rotation. So I need I. So what does I equal for both? Because I need to remind myself that angular momentum is I omega. So I definitely need this. So the key word here is that you're told that it's a disk, and then I look and I've been given the radius of both disks and their rotational rates. So I have that. Now what I can do is look at the table in my book, and I find that for a disk, I equals 1/2 mr squared. So my I here is going to be 1/2 times this 2 kilograms times the radius squared, this 0.2, and that's in meters, 0.2 meters squared. And over here, this I is 1/2 times 4 times, let's see, is 0.1 meters squared. Okay, so now I have that. Now we can write this out. Let's see. These are two things starting off separate, but coming together. Omega, these are angular quantities. Am I given the direction? I am not, but does it matter? They're both going in the same direction. So for this sake, I'm going to say that they're both rotating like that away. And I'm going to call that positive. So I know that they're both going to have the same sign. So we can go ahead and write out that our our angular momentum initial is going to equal our angular momentum final. And it's a collision inelastic, so I'm going to have I1 omega 1 plus I2 omega 2. They're sticking. That's the sum of my i's, I1 plus I2, and that gives me my omega final. So I can rewrite this. That I'm going to have, let's see, I1 omega 1 plus I2 omega 2 divided by I1 plus I2 equals omega final, or omega prime, however you want to define that. Now, one of the fun things I can do here, if I want to save on some of my button pushing, see my R's are different, but I have a 1/2 in each of these. So let's see, I have a 1/2 mr squared plus 1/2, omega 1, plus 1/2 m2 r squared divided by 1/2 m1, I forgot my omega again, mr1 squared plus 1/2 m2 r2 squared. Why am I doing that? Just to point out that one of the things I can do to simplify life, I have 1/2 in every gosh darn term. So that thing is just going to cancel out. So when I want to put things in my calculator, then I can just put in this 2 kilograms, radius squared times 0.2 squared. Omega 1 is 50 plus this mass is 4 kilograms times 0.1 squared times 200. That's my omega, those are my radii, and those are my masses. Divided by 2 kilograms times 0.2 squared plus 4 kilograms times 0.1 squared. Sorry, I should be consistent with my signs. There. So one of the tempting things here is you say, well, we just canceled out that 1/2. Can't they just cancel like these guys out and these guys out? Remember, these are sums. So I can't, because these two quantities are going to be added together and give me something different. I can't factor out this 50 or this 200. I mean, I could kind of simplify that a little bit, but it won't do me much good. So where I would have like just this term on the inside. So if I can't do that, then I can't simplify this anymore. But I can get rid of some of those ugly fractions. So we put that in our calculators and we get what? I put that in my calculator and I get 100 with ugly units. It's, let's see, kilograms, meters squared, omega per second. Is that what I come out with? Yeah. Yep. Yeah, for I. Yep. So I don't really like doing units on this because it just gets hideous. So we can see that, let's see, this slowed down. So we kind of like split the difference a little bit between these two. Let's see, this is the bigger mass and the smaller radius. And this one, then, yeah, moving slower. So it kind of feels good there. And there's one thing I want to point out, though. With something spinning, as far as conservation of angular momentum, it's kind of the downside of not being in class, is that we have these little wheels that we can take. And the wheels spin, and I can pick it up and sit down on a swivel chair and hold on to the darn thing, and I will start going in a circle because of conservation of angular momentum. Also, ice skaters, they're a great example. When they're spinning and they have their arms wide out, spread out, and then they pull their hands together, and then they go super fast, and I don't know how you don't throw up, but they don't, and it's amazing the speed that they get. But that's conservation of angular momentum. So they're taking their inertia, is what they're doing, is they're shrinking down that R. And so their initial and final then is dependent on how much they've shrunk that R, right? So I would have something for my ice skaters where it's just this I omega equals I omega. So if my final R is smaller, everything but the radius everything but the radius cancels out, and I end up with a larger omega. Pretty cool. So the one question I want to ask you to figure out yourselves is what happens if this one was rotating a different direction? So if instead of going both of them in this direction, what would happen if this one was going that away? Play with that and let me know what you come up with.